Biomedicine. In tissue engineering, cell biology and medical science, many applications become accessible through explicit control over molecular structure and mechanical properties, such as elasticity, cross-linking degree or surface morphology of certain biomaterials. In view of such applications, a combination of holographic and photolithographic processing may be used to create complex structures for micromechanical and photonic devices. Here again, volume holography in photosensitive polymers is of high interest for practical applications, with respect to the high flexibility and optimization ability of subsequent devices. The optical functionality can be applied for the use as holographic sensors. Photonic crystals are promising candidates for biosensors and bioassays. With view to the interrelation of function and structure, functional structures of different PC materials are linked with respective sensing mechanisms. Optical structures have already been incorporated in hydrogels for diagnostics. Bragg grating-based hydrogel sensors as well as hydrogel microlenses are utilized as optical sensors. In both cases, a significant change in the refractive index or rather high diffraction efficiency is required to ensure good functionality. Substantial benefits of holographic patterning concern the fabrication flexibility. Furthermore, hydrogels can also be structured photolithographically, taking advantage of diffusion processes. Three-dimensional structuring at the microscale results in the ability to spatially tailor biomechanical and biochemical material properties. Beyond the specific material characteristics, discussed in section 2.1.1, there are additional requirements for the composition of novel biomedical material systems, such as biocompatibility and non-toxicity. Investigations on cellular behavior on 1- and 2-dimensional surface topography may be used to evaluate cytotoxicity and cytocompatibility as a function of mechanical properties, such as the cross-linking degree. Selective cell adhesion and spreading can be observed, depending on the biochemical, physical and mechanical properties. For applications in tissue engineering and medical science, the desired functionality could be achieved with a combination of optical structuring of the volume and specific modification of the surface. With view to the possibilities of miniaturization, this could result in the design of advanced biomedical implants, sensing systems and diagnostic tools for in vivo studies. In particular, intra-ocular lenses, EOLs, implanted in place of the natural eye lens in ophthalmic surgery, open up the prospect of substantial improvement, such as to overcome the systematic induction of higher-order aberrations or to enhance the approximation to the original function of the natural eye lens. This affects not only the visual ability but also some more complex abilities of the eye such as accommodation, the capability of the eye to focus sharply on close-up and distant objects, or brightness-darkness adaptation. With regard to the design, diffractive approaches are feasible and highly favorable in many respects compared with conventional refractive designs. Systems currently in use are limited to surface patterns, providing combined diffractive-refractive structures. Volume holographic systems, with potential special features involved, have not yet been applied. However, the use of refractive-diffractive optical properties by means of an integration of volume structuring, in combination with surface modification could provide highest possible functionality and applicability. Besides design, performance and functionality, biocompatibility, especially in case of foldable hydrogel lenses, must be ensured. Prospective EOLs could fulfill their function with an optically structured volume, leaving the surface free for other functionalities. Thus, late postoperative opacification of implanted lenses, resulting in glare and misty vision, might be addressed based on surface modifications for specific bio-interaction. In any case, the integration of optical functionality into the volume of intraocular lenses might succeed according to the leading idea from structure to function and would be accompanied with considerable benefits.